Welcome to LabMiss.com in a lab video series on Cisco SD-WAN. This is Metha, your instructor for this video series. For a complete list of SD-WAN videos, you can visit our website under the routing switching section. There you can also sign up for our newsletters to receive the latest video updates. In the last two videos, we saw how we can manipulate routing information in the control plane using the centralized control policy. In this video, we are going to move into the data plane manipulation, which directly affects the actual packet using the third type of policy called centralized data policy. We will go through some scenarios that will cover different aspects of the policy to demonstrate things like access control lists, deep packet inspection, and traffic engineering. For our lab setup, we have three SD-WAN controller, vManage, vBond, and vSmart situated in the simulated internet, and these are their corresponding IP. 811.255.11.12 and 13 in terms of the system IP. We have four SD-WAN sites, site ID 1, 101, 102, and 103, with the ID 1 being the headquarter, and it has two ISR 4K. And the site 101 also has two ISR 4K, while site 102 has a VH Cloud, and site 103 is a VH 1000. Currently, they're all connected to two transport. One is internet and the other one is MPLS. The connectivity is up and running, and we do have the reachability across the overlay. On each of the transport, we have a restrict flag set, and I believe that was two videos back where we use it to make sure that the packet, when it gets sent in one transport, remains on the same transport when it exits the other end. So there's no cross-transport communication here. At each of the site, we have Windows machine that we can use for testing. At the headquarter, we got Windows 2012, the IP of 172.16.32.40. For the three remote sites, we have Windows 10 and Windows 7, as you can see right there, and these are their corresponding IP address. Right now, we do not have any policy being applied to our deployment, so the site can freely communicate directly between one another. Before we get into the lab configuration, there are a few things that you might want to know about the centralized data policy. As I have already mentioned, centralized data policy affects the traffic at the packet level, so some of the matching conditions will be based on the information inside the packet, like the layer 3, layer 4 information in the packet header or the actual packet content that might reveal the type of the application, and that's part of the deep packet inspection. The term centralized means that the configuration will be performed on vSmart, just like the centralized control policy, but because the packet processing is done on the WAN edge themselves, the policy will also be passed onto the WAN edge, right? And then stored in the read-only memory, but not in the actual configuration. But most importantly, the policy is applied from the WAN edge perspective in the direction between the transport or the service as a whole, and they can be, let me grab my pencil. All right, so that you can apply the policy in the direction of transport to service, which is considered inbound, the service to transport, and that's considered outbound, or you can do both. So as you can see right there, the policy itself is actually sitting in the packet path. One thing to keep in mind is that you cannot use the centralized data policy to control the traffic from transport to transport like this, or from the service to service like this on the same WAN edge. So first scenarios are going to be that we're going to try to use the policy to limit the communication between the remote site, which means that we're not going to allow anything like this, and we only want to allow the traffic to the headquarter, to the subnet 172.16.00/16. All right, so the communication will happen from the site to the headquarter only, and that's going to be using an ACL. Okay, so before we do anything, let me hop onto the Windows 10 test 1 and do some ping tests just to show you that we do have complete connectivity right now, both between remote sites and remote site to headquarter. So first I'm going to ping 172.16, let's see, 17.2.10, so that goes to site 2, Windows 10, or site 102 rather, and then ping 3.10, which is the Windows 7 at site 103. Okay, you can see we just did this. Actually, it's the other way around. This and this. And now I'm going to ping the Windows 2012. And that's working just fine. So let me bring up, to start our configuration, the web interface to the vManage. We are going to, let's see, maybe reuse this guy right here, the LM Central policy. So we're going to start by creating some prefix list that will match the headquarter subnet. Oh, and also, I guess I forgot to mention in the scenario, there's a diagram now, we're also going to want to allow access to the internet, not just the headquarter. So this guy can go all the way out to the internet. Go back to list. We need a couple of prefixes. Because we're dealing with the actual data packet, for the packet matching, we need to specify data prefix and not the regular prefix, because that's actually a route prefix. Okay, so data prefix, we're going to create dpfx for data prefix. This is going to be headquarter subnet 00/16. Okay, so we add that. And then in order to lock down the communication to just allowing internet, we're going to deny RFC1918. So we are going to create one more prefix list for that. RFC1918, which is the range for the private IP. So 10.0.0/8, 192.16.0.0/12, and 192.168.0.0/16, comma separated. Add that. Next, we need to create a traffic policy. Remember, topology deals with the control plane. For the data plane, centralized policy, you select traffic policy. And this is going to be traffic data. Create new. The way that we plan to apply this is going to be from service to transport. Okay, so we're going to name it accordingly. Data from service. Okay, click sequence type. Here you see different applications of the data policy. The difference between each type is the available attributes that you will see for both matching and setting. And those attributes will be only suitable for that type of application, which kind of make your life a little easier, especially if you're new to this. But if you know exactly what to do, you can just use the custom type, which includes pretty much all available attributes to give you the most flexibility. As we're dealing with ACL, we can select Application Firewall. We're going to rename this to, just to make it easier, I don't think I've shown this before, you can actually rename the sequence over here on the left. There's going to be a firewall rule to the headquarter. Which is kind of nice, so you can organize your rules a little better. Add a sequence rule. First, we are going to allow traffic to the headquarters, so that will be a simple destination data prefix match to the HQNet. Action will be accept. As you can see here, you can either do a set counter or a log. Let's go ahead and add a counter. And you need to provide the counter name. All right, we're going to go and give it ACL to headquarter. This is like an ACL hit counter, but you will get the number of packets and the traffic bytes that hits the rules, not just the number of hits. Save. Then we are going to add one more sequence type for the application firewall and rename it firewall to iNet. All right, so that will be allowing traffic to the internet. In fact, I'm going to add a rule here that will deny traffic to RFC1918, and then we're going to switch to the default action to allow everything else, which is essentially the internet. Sequence rule, destination data prefix RFC1918, and action will be drop. And then the default action to allow internet traffic is going to be accept. Okay, so it's pretty straightforward. We can click on the preview just to get a better sense of what's going on. It's going to be a top-down match, and just FYI, even though you have that sequence type group, it's not showing up here. It's just the actual rule that are listed. Okay, so it's still going to be one big policy. Right, the first sequence match, the traffic that goes towards the headquarters subnet will be allowed, and we'll keep track of the counter. Anything else that goes towards the private IP address will be dropped, and then internet traffic will be allowed. Pretty straightforward. Let's go ahead and save that. Now we're going to go ahead and repurpose our LM control policy, or actually central policy, not control, central. Okay, click edit. I believe we have some topology policies to attach to this, so we need to get rid of them. Let me try that again. There you go. Under topology, yep, we had that in the last video, I believe, so we can go ahead and detach just to clean it up. And then under the traffic rule, traffic data, we can import data from service. And to apply that, you go back to the policy application, traffic data. Go ahead and add the site list and VPN. So this is how you tell the system where and what you want to apply the traffic to, where being the site list. We have a site list created in the previous video called site spoke, which includes the site ID of 101 through 103. So that's what I'm going to select. It's going to be from service, just to make sure, as I explained earlier. It can be from tunnel, which is from transport, or from service. You can have it apply in both directions. For VPN, it's a mandatory field. I have the service VPN number 10, and that's what I'm going to select in the form of VPN list, again, created in the previous video. Go ahead, click add. Again, you can preview the whole thing. We've already seen the actual CLI for the data policy. Now we also see the list. Okay, here's the site spoke site list, 101, 103, VPN 10. And we're applying that against site spoke in the from service direction. Go ahead, save, and then just like any other centralized policy, we need to activate it. A quick note here is that the configuration is being pushed to the vSmart. So I go and get ready to log into vSmart and show you that. Let's see, it should be done already. There you go. Data policy we just saw earlier. Sequence 1, sequence 11, default accept, the list, the site, and click apply policy from service. Now I'm going to hop onto BR11 over here on the console. And do the show SD-WAN run. Yep, I guess you can't do that. Let me do a section policy. Okay, this is just to show you that the policy configuration doesn't really get into the policy section of the device config, as you can see. But where it's actually going to be appearing is when you do the command show SD-WAN policy. Let me show you option from vSmart. Okay, and that's the content of the policy that the WAN edge has received from vSmart. Okay, the direction will be from service. Apply to VPN 10, the two sequence that we have, default accept, and then followed by the list objects. Okay, so not in the config, but in some kind of memory. Now let's go back to our Windows 10 and see if those pings are still working. Just going to up arrow, ping 2.10, and you can see that it's no longer working. Right, because the policy is being applied, we're trying to ping, it goes through that and the ACL drops it. Let's try 3.10, not working either. Let's try the Windows 2012 at the headquarters, and that is working fine because we have an ACL rule right here that permits it. And then finally at the internet, you can see that is working as well, right, due to the default action. So the 2 ping that we did earlier is being denied by this rule right here. All right, and finally to look at the packet counter, we do show SD-WAN policy, and here we have the option for data policy filter. Okay, and you can see that so far there's 15 packet match, which equates to 1491 bytes. Okay, there's the name that we provide to it, ACL2HQ. Yep, right there, the counter names. All right, so just the basic ACL configuration with a destination prefix match. In our next scenario, we are still configuring policy to limit inter-site communication, but in addition to using just the IP address, like we did right here, we will be also using the port and protocol. So let's say that we want to allow share file and CIFS between the remote site, because right now everything is being denied. So we're just going to open that up to CIFS protocol. Again, before we start, do a telnet to maybe 3.10, and we know that CIFS operates on TCP 445, and you can see that it's not getting through. All right, so let's go back to our policy configuration. Traffic policy. Let's go ahead and edit that. Yeah, connection fail. Let's add the sequence type for the app firewall. Let's rename that to firewall to site, just to allow traffic between remote sites. And we're going to match for destination prefix, still using that. We're going to have the IP scheme for the remote sites to fall within 172.17.00/16. So as a side note here, you don't need to point it to a data prefix list. You can just do a ad hoc prefix configuration right here as well, which is what we're doing. All right, then protocol TCP number 6, and let's look for destination port right there, actually 445. Okay, don't forget to switch the action to accept and click add. Right, so that would take care of, again, I need my diagram back, clean this up. Let's say when the Windows 10 test 1 I think we're trying to talk to Win 7 test 1 at site 103. So that only takes care of the outbound traffic or initiated traffic, because we are applying from service to tunnel. Right? But we also need to allow the return traffic when our remote machine over here trying to talk back, and then what was the destination earlier would become a source for the return traffic. So we need to add one more rule for that. And the reason why we're doing this is because the ACL we're configuring here is not stateful, right? It is not acting as a stateful firewall. Then we need the source data prefix, same deal. Protocol, and then this time it'll be source port 445, accept, add. And the last thing that we want to do, remember the firewall to INET, we have it denying anything going to the RFC1918, so we need to reorder our sequence. Let's put this all the way up to the top. There you go. Firewall to site, headquarter, INET, preview it. Yep, and you can see allowing communication to remote site on TCP 445, and then the return, and the rest of these are what we configured previously. Go ahead and activate. Push out to vSmart. Make sure that BR11 receives it. Right there and there. So our policy has been updated on the router. Now we can go back and try that. Telnet one more time. Yep, you can see ports open. But if you're trying to ping, that should still be deny. Or if you're trying to telnet to other port, like the RDP 3389, that's not working. Let me actually try the actual protocol or application. And there you go, it pulls right up. Okay. So the ACL that we configured earlier to allow CIFS is working correctly. The next topic we are going to cover is deep packet inspection. All right, so the way that DPI or deep packet inspection works on the Cisco SD-WAN is very similar to any other system. In order to figure out what application a packet belongs to, it needs to see enough packets to figure that out, which means that the first few packets we need to get through the router. And once the router has determined the application type, then it can enforce whatever appropriate policy is configured on it. Now to demonstrate this in our third scenario, we are going to deny FTP, RDP, Dropbox, and let's say Netflix. And this is going to be for anywhere in our SD-WAN. Now the first thing that you need to do before you can even utilize the DPI is to enable the application visibility. And this is done under the localized policy, which is a little hard to find. All right, luckily we already have the localized policy applied to all of our WAN edge at the remote sites. Back when we did the localized control policy for controlling BGP route advertisement, so all we need to do is just to reconfigure that. Let me show you how to enable application visibility. On the CLI is actually very simple, just one command, and you'll see that in a sec. So actually policy, and that will be localize. Okay, localize policy WEdge. Okay, click edit. And you can see that's not right because the application name doesn't show up. Let me refresh that. There you go. And all you need to do is just check that checkbox application. All it would do is to enabling application visibility. You can preview it, and the command we're looking for is way down here. You don't need to pay attention on this old route policy BGP because that's irrelevant to what we're doing right now. Okay, we're just piggybacking the localized policy that's already applied to our WAN edge in order to enable that feature. Save policy change for those. I believe the policies are applied to these routers right here. So go ahead and push it out. For the headquarter ISR 4K, there was another policy over here, which is this guy. Go edit. Same deal, enable application. Can preview. Because this is an iOS XE, well, this thing wouldn't know, right? So go under, it should go under the SD-WAN config section of the router. Right, click save. Next. And let me make sure that the command shows up on the CLI. Look for the word visibility right there. Okay, so that should be no problem. Okay, we're looking for BR11 right here. So let me make sure that the commands actually get programmed into the router. Show SD-WAN running, and we're looking for the app visibility. Yep, right there. Okay, so it should be on this router already. And with that command in there, the router should start inspecting the traffic and determine the application. Okay, so we need to validate that and make sure everything is working before we go ahead and configure our policy, right? And that the router can identify the application correctly. On our Win 10 test 1 over here, we're trying to FTP to our Windows 2012. You can see that is a success. And while I'm doing this, let me go ahead and log into. You can do a show command to see the actual traffic, and the command is show SD-WAN app forward DPI and flows. Okay, so if you enter that, let me try it again and make sure. There you go. That worried me a little bit. That didn't show up. Okay, so you get, let's just pick one and kind of go over that real quick. So you get the VPN that's coming from source destination IP address, the port, DSCP value, then the protocol number. For statistics, you get total packets, bytes, start time of the flow, ingress egress interface, the application, as you can see right there, is FTP, that's been identified, and the categories of the application, which is file transfer. In this case, the source is this guy, right? Win 10 test 1, 172.17.1.10, going towards the 32.40, destination port 21, and has been identified as the application FTP. All right, there's some of the ones you're seeing, 137 NetBIOS, 53 is marked as Microsoft Services. Type web. Okay, so we're good with FTP there. Next, let's try web application this time, Dropbox. So let me bring up Chrome. And just to make it a little bit easier, I can do a filter on just align the application. Okay, so you got some Google services because it just brought up Google Chrome. Now let's go to Dropbox. Okay, let's see if I have that. There you go. Here's the Dropbox. The majority of those, if they're SSL encrypted, obviously it can only show as SSL. Well, I mean, try to his best ability to figure it out, but worst case, show us SSL. But at least it was able to identify Dropbox. We saw some, well, Facebook, Yahoo, Twitter, all sorts of web app, right, LinkedIn. But at least it was able to pick up Dropbox. What about Netflix? Okay, the page loaded, and you can see it picked up Netflix as well. Now, what about if you're trying to RDP from Windows 2012 to the Win 10 test 1.10? Connect, just leave it on the login page, or prompt is good enough, hopefully. And what we're looking for is, do we see RDP? I think RDP shows up as the MSWBT. It's not really called RDP. Okay, so we've got that too. So it seems like the 4 applications that we have here, FTP, RDP, Dropbox, and Netflix, have been correctly identified by our router. Actually, let me show you the fact that was called WBT. Let me try it again. Yep, so we'll filter based on the port 3389, and as you can see, application is MSWBT, then client. Application family. Now, to configure our policy, the first thing we need to do is to create a list that includes all of the application we just talked about. That would be list, application, new application list. We're going to call this app deny list. And we can just search for it. We're looking for FTP, but on here it shows up as file transfer. So we'll pick file transfer protocol and data. And then, funny enough, it shows up here as RDP and not that MSWBT. Dropbox. Okay, so we got that, and Netflix. So we got all that. Go ahead, click Add, and we've got our application list. Then we can go back and modify our traffic policy rule. We're using the same policy. Okay, we can have a few places we can add this to. I'm just going to put it under firewall to HQ sequence, add another rule, and this will be application-based matching. So click application, select the list we just created, app deny list. We want to certainly drop it. Okay, so there's nothing we need to change there. Save that, and just to show you the reordering of the rule, because obviously that wouldn't work the way we want it, because anything that goes towards the headquarter subnet will still be allowed. So we definitely want to put our deny on top. Sometimes it gets a little tricky to get it up there. Let's see if I can pull this down instead. There you go. Okay, so deny is on top now, followed by the allow to the HQ network. Click on preview. So we're still allowing the SIPS protocol between the sites, the remote sites, and then it will be denying the app. So I guess, yeah, it doesn't matter because these app wouldn't match these rule anyway. All right, I was going to say that technically we can put this deny all the way to the top, but it doesn't matter in this case. Then deny the app. Doesn't matter where it goes, site to site or site to internet. All right, and then the rest of the policy. Hit save and activate. Push it out. Make sure that BR11 receives the policy. See if it's there yet. Not quite. I guess we can expect to see a little console output when the configuration comes down. Or maybe not. Let's see. Oh, never mind, yeah, because the config comes through the vSmart and not the actual vManage. Yep, there you go. So we got our app deny list, action drop. Now try to do the FTP again. Okay. It looks like it's failing right now because we're not getting the username prompt. But notice the first few lines being displayed, okay, while the router was trying to determine the application. So like I mentioned earlier, it has to pass, let the few packets pass through. Right, in this case, it contains all these metadata at the beginning. Right, but as you can see, sometimes you keep trying this, you might get all the way to the username prompt and even get dropped to FTP command line. In this case, not denying me. Yep, there you go. At some point, I guess when it collected enough data to declare it being FTP, this time it took a lot longer, because you actually allow some activities going on through the FTP. But eventually, you can see that it gets killed by our deny rule. Yep, connection close by remote host. So just a little caveat that you might need to be aware of, and that's a good way of showing it. All right, now let's try Netflix. I'm going to refresh that. Let me see if we can still do the show application over here. Yep, even though it's getting dropped, it still show the application being detected. You can see that the page is not loading now because we have Netflix blocked. And we can try the same thing on Dropbox. Yep, we do see Dropbox right there. And the page for Dropbox is not loading up neither. Finally, last application is RDP. Let's try that. We're not even getting the username prompt this time. MSWBT shows up, so it was able to recognize the application correctly. Hence, we're not getting there you go, getting denied already. All right, so that's deep packet inspection for you and how it works on the WAN edge device. In our next scenario, we are going to talk about some traffic engineering capability with the data policy. We saw in the last video that we could perform some traffic engineering by using the centralized control policy to manipulate the route next hop TLOC based on the matching route prefix attributes. But with the centralized data policy, you can do something very similar to that, except that we are not touching any routing table, but instead we are going to be forcing the individual packet to go certain ways after an ACL match, which technically gives you a little bit more granular control, as you can match by information inside the packets now, right? It's just based on the route prefix and attributes. You can say this is very analogous to the classical policy-based routing on the Cisco router or a PBR. Now, to demonstrate this, we are going to, let's see what we're going to do here. Maybe we'll force the traffic from BR3 to go to the headquarter first in order to get to BR1 or BR2. So somewhat kind of achieve the hub and spoke topology. Okay, so the way it's going to work is we're going to write a policy right here. So when the packet comes along, right, we'll perform whatever matching conditions that we want to do, and then when there's a match, we're just going to dump that packet into the tunnel that point towards the headquarter. Okay, once it gets to the headquarter should perform the regular routing and pass it back to whatever the final destination is. So let me do a little bit of cleanup work, because we still have ACLs and all that blocks remote site traffic. Go traffic policy, traffic data. From service, I'm just going to delete all this firewall because we're pretty much done with the firewall exercise. So delete, 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 and the default is allow. Okay, so you can preview it. The other thing that we are left with is the accept packets or accept action. Next, configure. Okay, we're going to be doing the testing from the Win7 test one, so let me switch out the test machine here as well. Right there, Win7 test one. Yep, it's all done. Let's do some tests. I'm going to ping the PC at site 101, 1.10. You can see it's pingable, and we can also note the latency or the round trip of 1 millisecond. Let me try to do trace route to the same IP. And here, the packet pretty much goes direct. So the first hop is the BR3, then the second hop is the BR1, and then the final destination, right? So right now, the packet goes from here over the tunnel directly to there. And we can try the site 102 as well. Okay, so next hop is 172.17.2.1, which is basically this guy. All right, and then from Win 10 test 1, let me try to trace route from there too. Yep, that's also 3 hops, and it goes like this. All right, so now let's go ahead and begin our configuration. First thing is to create more list for prefix match. The condition that we're going to use to match the packet coming in to the interface or through the router is basically just the destination prefix. Okay, that and that. So we need to create a list that will match that. List data prefix. Just pick the destination prefix because it's pretty straightforward, but you can pretty much use any condition that you see in the second, whether it's if you want to do all the way down to port and protocols, you can do that. If you do based on a specific source IP address, you can do that too. So again, basically very similar to the policy-based routing. Add that, dpfx. This would be a BR1, BR2 net 10/24 and 20/24. Save. Then we go to the policy. Once we have the list, modify the existing policy, add the sequence type. Here we are going to select traffic engineering. Okay, description is direct control traffic along a desired path. No, I should say control though, because it's basically data packet. Add that, add the sequence. Okay, add the destination data prefix, which is what we just created, BR1, BR2. And in fact, because we only want the policy to affect a Site 103 traffic, we're going to add the source prefix as a condition as well. Because we want to keep the direct communication between the 101 and 102 sites. Okay, it's the same policy. Remember, the way that we have the policy applied right now from vSmart, it's going to be pushed down to all of the remote sites. All right, so we don't want the policy to affect the traffic coming in from these guys. Which means I can go ahead and also condition based on the source data prefix. Since I don't have a prefix list created for that, I'm just going to do ad hoc. The action will be accept. Then in order to redirect the packet to your desired next hop, you can pretty much go ahead and set the next hop T-lock. Okay, you can select T-lock. And if the next hop router possesses multiple T-locks, then you probably want to list them all right here, unless you have a specific reason to only send the traffic to a particular T-lock. All right, but if you do it ad hoc, as you can see, it appears that you can only add one next hop with T-lock color encapsulation. But what we have here is two headquarter routers, R1 and R2, and each actually have two T-locks. Instead of doing the ad hoc, we are going to use the T-lock list. Okay, and if you watched our previous video, you should have seen us created a T-lock list for our headquarter. right there, which contain all 4 of the TLOC right there: internet, MPLS, internet, and MPLS. And we do have, I don't know if you notice it, I guess let me do it again. On the right hand side, we have 200, 200, 100, 100, 200 being the TLOC preference being set for MPLS. So I guess when we go through the verification, you see that hopefully the packet will use the MPLS first. Right? It should be as simple as that. Very similar to when you do the PBR, when you set the next hop IP address. Here we're dealing with the TLOC, right, as a next hop. Go ahead and save. What do we miss here? Oh, yeah, we need a VPN. Okay, so we're trying to save that, but it complains. When you configure it in traffic engineering, it looks like the system wants you to specify VPN as a matching condition as well. So let's go ahead and do that. Actually, setting. Yep, not matching, but setting. I was looking for that. Okay, so this will be for the VPN 10. Save and preview. Once again, it will match the packet sourcing from 172.17.3 going towards the BR1, BR2 subnet. Will be allow inside VPN 10. And we are overriding the route TLOC with our own TLOC list right here, which points to the headquarter. Go ahead, save and activate. All right, let me log into BR3 and do a show policy from vSmart. There you go. Yep, I guess we can go through that together. Kind of get expanded out for us right here. Direction will be from service. The first sequence, source destination, and then these are the TLOC that we are setting. Okay, so that's dot 11 is the HQR1, dot 12 is HQR2. Each has the MPLS and internet, and we are preferring MPLS. There and there. Right, that's basically the content of our TLOC list. All right, so now let's go back to my Win7 test one. Get ready. Okay, get rid of everything. And do a ping again that we did. Okay, one thing to notice is that the latency kind of shot up to 20 millisecond. Before it was just 1 millisecond, and now it's kind of 20, 21, 22. Okay, and the reason being is that the packet now is forced to go through the headquarter MPLS, and because I have a WAN simulator right there, that adds 10 millisecond one way, right? So it round trip means that it also probably comes back through MPLS. Actually, it goes like this. Let me draw this right. But from here, I can't tell if it goes through R1 or R2 until I do a trace route. But anyway, it goes through MPLS at 10 millisecond. So when it hits R2, then either R1 or R2 has to send to BR2. And if it decides to choose MPLS to do that, then I guess that adds another 10 milliseconds right there. There you go. I was trying to figure out how we get to the 20 millisecond because it traversed that link right there twice at the headquarter. Then the R2 will just send the packet straight back to R3. Hence, we not have that added 10 millisecond. All right, cool. And we can do a trace route there too. There you go. So it looks like it goes to 10.0.1.2, which is the HQR2, right? Which is exactly how we have it drawn up on the diagram right there. That's an extra hop. Before it was just 3 hop, now it becomes 4 because the HQ is now an extra hop. Let's see if that affects the traffic going to the Site 101 as well. Yep, same deal. So it looks like traffic going to Site 101 actually went through the HQR2 also. Because 10.0.1.2 is the WAN IP right there. And we have an extra hop. Okay. But now if we try to redo the trace route from the Win10 test 1 back to actually Win10 test 2 at site 102, basically just rerun that same command right there. Because our policy should not be affecting anything outside or coming from outside of the site 103, then yep, we don't expect to see the extra hop from here to here. Okay, so that still remains a direct communication, even though the policy also gets applied to pretty much all these routers right here. What we can also do, other than the ping and the trace route, is to go to the simulate flow tool for the BR3. Simulate flow, VPN, provide the IP going to 2.10. And we're hoping to see, yep, even though there are 4 available paths, right, only the 2 that belongs to MPLS are being selected because of the better TLOC preference. Okay, and the next hop is pointing to the headquarters, which is exactly how our policy is written. All right, and like I mentioned earlier, if you go to the BR11 at site 101, and they show SD-WAN policy from vSmart. All right, we see exactly the same policy on BR11, even though the policy won't match any traffic coming from there, right? Because we did say source IP 192.168.217.3.0. But because this is the centralized policy, right, the data policy, all the WAN edge that have the policy applies will get the same exact policy. All right, let's try one more traffic engineering scenario. Let's say that we want our traffic from BR3 to always prefer the local MPLS circuit to get to the headquarters, right, as long as that circuit is up. We saw in the past video with the centralized control policy that we could only control which remote color the router will end up using by changing the route and the TLOC preference in order to influence the traffic routing, but not the control over the local color. With the data policy, you can actually force the traffic out certain color or circuit. Before we do anything, let's go back and rerun a flow simulator going to the headquarters. Simulate, and right now, as you can see, it's using all available paths, both internet and MPLS, load balancing 4 ways, okay, to both routers, HQ R1 and R2. So now we're going to make the router prefer MPLS. Let's go back and modify our policy. Should be a very simple configuration. Hopefully you guys can get a hang of this already. All right, so that's traffic going to the remote site. We just need to add one more rule for traffic going towards headquarters. Let's say we only want to, again, affect the BR3 site and not the remaining sites. Which means that we're conditioning again based on the source data prefix. 172.17.30/24, and for the destination prefix, it's going to be the headquarter network, which I believe we already have one created right there. Conditioning on the source prefix and the destination prefix. For the action, we need to accept, and then you can simply set the local TLOC color. As you can see right there, local TLOC list, and that would be MPLS. All right, you have an option to do encapsulation as well. I'm just going to leave it blank. And then at the bottom, there's a restrict option. The restrict means that you want the packet to be dropped if this particular transport or color is not available. Okay, so basically just lock it down and make sure that the packet that matches this rule can only go out the circuit and there's no failover. Go ahead, save that. Preview. Source, destination, set color to MPLS, and that's it. Go ahead, save. And when it's done, we can rerun the simulation and see what that looks like. Okay, so that's done. Right there, before we have 4 path, what we expect to see is, there you go, we're just down to 2. Only use MPLS to get to the headquarter, whether it's via router 1 or router 2. All right, but let's say if we change that to internet, because it's not matching the policy we just configured, it's still using all of the available path. So that's how easy it is to match packet and kind of force it out a particular transport color. For the next scenario, we're dealing with failover. Because we've been forcing the packet to be sent to a specific next hop, right, back in when we did the redirection to the headquarter and to the BR2, you probably want to know what happened if that next hop becomes available. In other words, if your headquarter router goes away or the circuit goes away, and whether or not if the packet would be black hole. Okay, so what we're going to do, because we still have that policy configured, from BR3, let's go to BR1 or BR2 to traverse headquarter. What we're going to do is to take down the headquarter, internet, and MPLS, and let's see what happened. I'm going to go ahead and shut down the interface that connects the router R1 to the internet and router R2 to MPLS. And because we have the TLOC extension between here, that should essentially take down the second transport on each of the router as well. Okay, and I believe the interface for those 2 devices that connects to the transport is 101 and 104. All we need to do is shut down, and the ping that was working earlier. Let's see, which one were we doing? Nope, we want the Win7 right there. So earlier I was able to ping 1.10. Let's try that again. And you can see that it's not working anymore. So we're trying to rerun the flow simulation. You can see that there's no available next hop, and that's why the packet is not getting routed anywhere. So when the basically packet hits BR3, go back over here, packet hits BR3, there's a policy that said please send to the TLOC that belongs to headquarter. Okay, but because we shut down all the circuits, that essentially took down the IPsec tunnel because the BFD would have timeout, then the BR3 would not have available routes to that. So it just basically dropped the packet. Yep, so indeed the traffic will be black hole if all of the next hop TLOCs are down. Okay. Let me bring that back up and we should see the ping comes back. There you go, fairly quickly. All right, so what about what we did earlier with forcing the local circuit out the MPLS? Okay, so we had the BR3 pick the MPLS as the first choice in order to get to the headquarter subnet. Right, so now what happened if that MPLS circuit goes away? Let me rerun that again. And this is going to the Windows 2012 at the headquarter. All right, so we got MPLS, next hop, our circuit being used or path being used to get to the headquarters subnet. I'm going to go ahead and restart my ping to 1632.40. And now I'm going to go ahead and shut down the MPLS on BR3, I think. Let me see. Yep, so I'm going to take down the MPLS right here, right, the circuit. Let's see if the failover will happen or not. Ping's still going. The interface is 15. Okay, it's BR3 interface. And shut. Let's see what we get. Okay, 1 ping loss, 2 ping loss, and then it recovered. So that tells us right there that some kind of failover happened. And if we rerun our simulation, you can see that it picked up the internet path instead. So you can see that the default behavior for this, if you kill the local circuit on the router, of which you have the policy force the traffic out of, if that circuit goes away, then it's just going to look for other available path. Okay, no shut. What about if this is a remote failure? Remote failure being, instead of it being a local circuit, it's the remote circuit. Okay, so we can try to kill the circuit right there on the, actually I'm going to shut that interface down on HQR2. See if we get the same result. Okay, and by the way, you can see, let me stop that real quick, the latency change. If you've been watching our videos and you know that usually when you get the low latency like that, when you go to headquarters, it means it used the internet. And because we just bring the MPLS back up, the latency went back up to 10 or 11 millisecond or so, right? So we know that it actually passed through the MPLS now. Let's keep the ping going. I'm going to shut down interface on our HQR2. Go ahead, shut. And this is again the remote failure. 1 ping loss, 2 ping loss, and again recovered with 1 millisecond latency, which means that it has already failed over to the internet. Okay, I'm not going to run the simulations or anything. Bring that back. The last thing I want to test here is that restrict option that I pointed out when we were configuring the policy. Oh, I don't know why I did that. Just accidentally sign out. Back in. Okay, go to policy and then traffic policy, edit. Let's find that rule. This guy, and we're going to select on restrict. Remember what I said about the restrict flag? It means that if the circuit is unavailable, it will not try to find another available path. Make sure save and save. So now let's try to fail over again. Okay, so we're still pinging using MPLS. Getting ready to shut down. I'm going to go back to shutting down the local circuit. Okay, ping is underway. No shut. Actually, shut. Okay, 1 ping loss, 2 ping loss, and this time we've got nothing. So failover did not happen, and that's why this thing is black hole. I guess I can rerun the simulator too. Yep, and we do not have any backup path show up on here. Okay, and that's the effect of having that restrict flag set. No shut. All right, so from this you can see that setting local T-lock or color still allows the transport failover unless the restrict flag is chosen, while setting the remote T-lock, right, which when we did the T-lock overwrite, is pretty much the hard code with no failover. So just keep that in mind. Let me do a cleanup by deactivating the policy just to get ready for our next lab. Yep, deactivate. Right, so that was the centralized data policy, although we didn't try the direction from the transport to service, but the idea is the exact same. Also, we only touched upon some of the capabilities here, mainly the ACL firewall and the traffic engineering. The other capabilities like QoS and service chaining or NAT that you might have seen when we trying to configure the policy will be covered in a future video. And that wraps up our video on SD-WAN, ACL firewall, and traffic engineering using data policy. You can visit our website to view an extensive list of our lab videos and sign up to get access to additional lab contents. Thank you for watching LabMiz.com, and I'll see you guys in the next video.